Welcome back, Focus Learners, to another explainer. Today, we're diving into a genuinely thrilling quest to solve a 60-year-old physics hurdle. We're talking about the absolute holy grail of materials science, achieving ambient pressure, room temperature, superconductivity. The source we're analyzing today lays out an incredibly innovative theoretical pathway to finally make this happen. And the secret, well, it lies in a very specific type of metallic glass. Let's get right into it.
So think about this for a second. What if we could trap the most elusive state of matter inside a tiny piece of glass? The stakes here are absolutely massive. A room temperature superconductor would fundamentally revolutionize everything. Our power grids, our electronics, global transportation, basically our entire relationship with energy. But there's a huge catch. The material we actually need to pull this off, metallic hydrogen, is notoriously impossible to hold on to at normal everyday room pressure.
To understand why, let's look at the timeline. Back in 1968, the brilliant physicist Neil Ashcroft predicted that atomic metallic hydrogen would be a high-temperature superconductor, entirely because of its strong electron-phonon coupling. But look at the massive gap between that prediction and our next real milestone. It wasn't until almost 50 years later, in 2017, that scientists Diaz and Silveira finally synthesized it in a lab. But here's the crushing, heartbreaking frustration of modern experimental physics. They successfully made it, but the literal second they released the pressure, the sample vanished. It just immediately reverted right back to a molecular gas. And that brings us to this massive number, 400 gigapascals. This highlights exactly why metallic hydrogen is so incredibly difficult to study. To even force hydrogen atoms close enough together to enter a metallic state, you need pressures exceeding 400 gigapascals. To put that into perspective, that is millions of times standard atmospheric pressure. We're talking about the kind of crushing pressure you'd only find deep inside gas giant planets like Jupiter. Down here on Earth, this state is thermodynamically unstable at low pressure. The metallic phase only exists when it's actively being crushed.
Okay, let's dive into exactly why that happens. Section 1. The barrier, the metastability problem.
We really have to understand why metallic hydrogen just instantly reverts to a gas when the pressure drops. Why can't it just stay solid? Well, it's all about how the surrounding atoms are arranged when we try to recover the sample. If you try to trap a phase inside a standard crystalline matrix, it acts like a wide-open highway. A crystal's orderly, periodic structure provides low-energy coherent pathways. These pathways essentially let the hydrogen atoms quickly recombine and escape as a gas. This molecular nucleation happens in mere nanoseconds. But an amorphous matrix, like glass, is completely disordered. It lacks any long-range order. It's essentially a chaotic molecular maze that totally frustrates atomic rearrangement, blocking those coherent escape routes.
Which leads us perfectly into Section 2, the hack, trapping hydrogen in PDI, P-glass.
This proposed workaround is honestly awe-inspiring. It relies on kinetic trapping using a very specific metallic glass, palladium nickel phosphorus, or PDNiP. By using this amorphous host matrix, scientists can theoretically create the ultimate microscopic prison. The hydrogen is forced into a metallic state under high pressure. But when you remove that pressure, the chaotic glass structure traps it right in place. So why is this specific glass the perfect candidate? 4 reasons. First, it's a proven bulk glass former, with a slow cooling rate, meaning we can actually make centimeter-sized samples. Second, the palladium acts like a massive sponge. It has incredibly high hydrogen solubility, giving us plenty of nucleation sites. Third, there's a vital electronic handshake. The D band of the palladium perfectly overlaps with the S band of the hydrogen, facilitating that metallic bonding. And lastly, high thermal stability, giving scientists a wide, comfortable temperature window for processing.
Now, because of the disordered nature of this glass, it creates this really rough energy landscape filled with many local potential minima. Basically, they're little atomic cages with ideal interatomic spacings. When hydrogen atoms get trapped in these cages, they face an activation barrier of 0.2 to 0.3 electron volts. In thermodynamics, this is the magic number. This barrier is just high enough to kinetically trap the hydrogen atoms. At room temperature, the atoms simply do not have the thermal energy required to spontaneously overcome that barrier, recombine, and escape. They're stuck.
Now, what's really interesting about this next part is the math. Section 3, the math, transition temperature estimates.
Now that we've theoretically trapped it, we obviously need to know how it's going to perform. Using Neil Ashcroft's original Macmillan equation framework, we get a baseline estimate for our trapped metallic hydrogen, 70 to 110 Kelvin. Because the hydrogen is now sitting inside this much heavier glass matrix, its effective Debye frequency is reduced compared to just pure metallic hydrogen.
Now, sure, 70 to 110 Kelvin isn't exactly room temperature just yet, but it is crucially above the boiling point of liquid nitrogen, which sits at 77 Kelvin. That is a huge deal because it makes it highly accessible for real-world cryogenic applications using the tech we already have today.
But it actually gets even more fascinating. There are 4 specific enhancement mechanisms at play inside this glass that can push that transition temperature even higher. First, confining the phonons inside those tiny glass cages enhances the low-frequency modes. Second, that palladium D band we mentioned, it increases the density of states at the Fermi level. Third, the shear amorphous disorder itself creates localized electronic states that can actually boost electron-phonon coupling. And lastly, the glass matrix exerts a slight negative pressure or tensile stress on the trapped hydrogen, which softens the phonon modes and further enhances the superconductivity.
So when you factor in all 4 of those specific glass matrix enhancements, the new transition temperature estimate jumps to a massive 100 to 180 Kelvin. This jump puts into perspective just how much closer this matrix hack brings us to the ultimate goal of ambient pressure, room temperature superconductivity. We are literally starting to cross temperature thresholds that would completely rewrite what is possible in modern materials science.
Let's ground this theoretical physics in reality. Section 4. The verification, experimental protocol.
To definitively prove this kinetic trapping actually works, the source outlines a proposed $1 million 24-month physical experiment. The protocol breaks down into 4 really precise steps. Step 1. Synthesize the bulk PDNIP metallic glass using arc melting. Step 2. Electrolytically load the glass with hydrogen at ambient pressure. Step 3, take a microscopic piece of that loaded glass and compress it in a diamond anvil cell up to between 100 and 200 gigapascals. This is exactly high enough to force the metallization, but crucially, it remains below the point where the glass itself would crystallize. And finally, step 4 is the trap. Rapid decompression at 10 gigapascals per minute to lock the metal into its solid state before it ever has the time to nucleate back into a gas.
So let's impartially look at the probabilities of success for this protocol. The source estimates a 30% probability of a massive breakthrough, meaning we trap the metal with a transition temperature over 100 Kelvin. Then there's a 40% chance of trapping it with a lower transition temperature. That would still be completely monumental, as it would be the first ambient pressure metallic hydrogen ever created. Even a 20% chance of partial metallization yields incredibly valuable new physics data regarding confined hydrogen. And hey, even if it completely reverts back to molecular gas, that 10% scenario, it simply means the glass structure requires further optimization. Every single outcome teaches us something absolutely vital. Which brings us to a critical question. If the trapping works, how will scientists definitively prove they've achieved superconductivity? They'll rely on 4 established verification tests. They'll use squid magnetometry to check for the Meissner effect. They'll use a 4-point probe to confirm a sharp drop to 0 electrical resistivity. They'll use adiabatic calorimetry to look for the classic BCS jump in specific heat. And finally, they'll test the isotope effect by swapping the hydrogen out for deuterium to confidently confirm the underlying electron-phonon mechanism.
And that leaves us with a truly profound realization to end on. If this kinetic trapping paradigm is successful, this amorphous metallic glass effectively acts as a universal pressure memory. Think about that. It records the high-pressure state and brings it safely back to ambient conditions. And that begs a really provocative final question. What other impossible materials will glass pressure memory unlock for us? Could we soon see high-pressure superionic ice or dense metallic carbon just sitting safely on a lab bench? The future of advanced material science might literally be trapped inside a piece of glass, just waiting for us to unlock it. Thank you so much for joining me on this explainer. Keep feeding that curiosity, and I will see you next time.